Welcome to a brand new episode of Zeroing In. I'm Naman Jain, and hosting this episode with me today is Garima Agarwal, who recently completed her master's in aerospace engineering at Caltech and has worked in the field of trajectory optimization and low Earth orbit constellation designs, much of which has been in strong collaboration with our guest for today. In conversation with us today is an illustrious scientist from the Indian Space Research Organization, or ISRO, and a veteran in the industry of space sciences. One of the pioneers in the Indian chapter to have explored the dynamic field of spaceflight mechanics and astrodynamics, he pursued his bachelor's in mathematics and master's in applied mathematics from the Madurai Kamaraj University. Following this, he joined the Vikram Sarabhai Space Center in 1984 as a scientist and served for a span of 26 years, during which he worked on a plethora of distinct applied research disciplines, broadly covering the integrated aspects of space mission design and analysis, orbit raising and maneuvering studies, and optimization, with main focus on transfer trajectory design for various space missions. Among his numerous significant contributions, he notably served as the deputy project leader of the mission division for the Moon Impact Probe project of the well-known Chandrayaan-1, or the moon mission of ISRO. He also planned the Mangalyaan mission to Mars and is the crucial person behind the fundamental idea of multi-satellite launches that ISRO currently uses and employs. He shifted to academia in 2010 and took up the role of an adjunct professor in the Department of Aerospace Engineering at IIST. His intimidating brilliance and ingenuity is strongly complemented with great warmth and humility. In our conversation with him, we discovered more about his journey and heard further on his insights and perspectives of an exceedingly fascinating and equally challenging field of space exploration in this present context, and what it takes to literally shoot for the stars and beyond. Extending a very warm welcome to Dr. R.V. Ramanan. So, good morning, sir. We'd like to start with a discussion about your formative years and what did your childhood aspirations look like, or if you had any role models while growing up?
Childhood, I didn't have much role model or anything. Nothing was there, to be honest. I was from a village. I was born in a small village, and we were all brought up in village atmosphere. And I was studying in a government school, in a small school, in the very nice environment. Unlike you people, we were all playing for the most of the time. We were not studying. Studies, then tuition, studies, tuition. So we were enjoying life probably. So we did not have time to think of anything else actually. Only I started thinking after getting out of the school, and maybe when I entered college, then I started looking at the people, mostly my teachers. Actually, in my opinion, these role models can be from your surrounding only. Maybe somebody else can be, you can call them as like Yakalaiva had a Dronacharya, that type of relation it can be there. But we do not know them directly, what are their real characteristics and all. So he was Venkatachari from my college. He taught me astronomy actually. I used to think I should teach like him, not now, long ago. But he is a person, he had an influence on me to work on space-related problems. Actually, I didn't know what I have to do, but he is the man who induced that type of thinking in me. I should work on space missions.
Yes, sir, this is a curious bit, and I would like to follow up here. You say that you had these professors in your college who were quite inspiring. And you were studying mathematics as well, right? So how did these two things come together for you? Like researching on space-related topics and fundamental mathematics. Did you have this at the back of your head that you wanted to take this up together?
To be honest, I didn't know what I have to do. I want to be a space. I want to work in space. I want to be a scientist. At that time, people believed engineer means he will be involved in construction. And I also thought so. Actually, being from a village, I also thought being an engineer, I will be involved in some type of field activities, which I said I am not for that. I want to be a scientist. Then somebody told me you have to study your master's in science. So then I went on. So my luck led me to a college to do my master's, where the spaceflight mechanics is taught. Maybe that is the only college in whole of South which teaches spaceflight mechanics, one of its subjects, 4 subjects actually. That is one thing. So I had exposure to spaceflight mechanics even in my master's days. So then I thought I took a right decision to do masters in that. So actually for any subject to do design, strong mathematical background is required. Though I had all eligibilities to become an engineer, mark-wise, all this, I never thought of that thinking. Many of my parents, like you people, are influenced by your parents. You should do engineering. Never, my parents never did with me whatever they left. They also never, too much of interference is not there, of course. Whatever life takes on, it went on. Actually, that's why I believe in God. God led all to this type of thing.
This is quite interesting to know. And there's this continuing idea of carefree discovery that stands out. Taking this towards a technical side, we'd like to discover more about how you continued this pursuit further in the initial years of joining the Indian Space Research Organization. Looking at your research works, such as developing analytical algorithms for lunar and interplanetary transfer trajectory designs, lunar descent and ascent missions, halo orbit transfer trajectories, low thrust optimal transfer trajectory missions, low Earth orbit constellation designs, to name a few of these. These are extremely intimidating topics to look at from the outside of the field, and I'm sure quite challenging to take up as well. Can you talk about how this flow took on for you?
Yeah, when we joined, actually, unlike now ISRO, not many launch vehicle missions were there. Only once in 3 years, 4 years, there used to be launches actually. So once we do the job for that to meet that missions, we had lot of spare time, and how to spend that spare time we had to think. This obviously is research. We have to do some research actually. Actually, my boss used to tell me, if you do your regular job, you are getting salary for that. If you want promotion, you must do something extra. That is what research he meant. So that type of thing, motivated us to do research. People around us actually were research oriented, and now I think ISRO is harvesting that type of people, that thinking, all that. So now if we do now research, then future people will be harvesting. That is what is, always we know those who are planting tree may not be enjoying that, or that fruits will be enjoyed by somebody else, isn't it? Future generations. It's something similar to that. So 84 I joined, and 84 immediately after some training, all that. I went to my boss and I said, I want to work in this interplanetary mission. Then he was taken aback. Okay, fine, you start. Nobody knows where to start. That is the one thing. Nobody knows. So unlike this time, you give keywords, it searches and gives all types of information, right? Many of them unnecessary. Certainly some useful information you get in the internet. But at that time, we had to go to library to search for things, what is available in the literature about what we think about. I spent a lot of time, and it took almost 1 year for me to know what I have to do to reach other planets. That is a type of knowledge it was not available. Now today, my students will do it in 1 month, less than 1 month. That is the technology and the knowledge growth actually. Yeah. So first we started with interplanetary mission. When I said, I went on reading. Then finally I had to realize that I have to solve Lambert problem. And I had JPL reports actually. JPL reports means that the mission opportunities are listed down, not methodology. They don't talk about how to solve, how do you solve that problem, how do you arrive at the solution. They just a compilation of the data analysis actually, the opportunities and the related details. I had that book certainly. So Earth Mercury was the first one I generated actually. That's a thing. So when I generated, I went to my people, my boss, and I told that I got exactly one line I shown. This line I could exactly reproduce. So then he was overjoyed and he called immediately all people here. Come, there is something here JPL could do. We are able to do here. You come and we are. It was that moment was very enjoyable. That is a type of encouragement we got. All the people were so happy. So then it went on, and slowly we expanded to all other things, interplanetary. Then it went on. And then later on, the idea came, India may not go for interplanetary mission, but instead it may go for moon mission. Then I started, but already I had the background, so putting them into moon mission, it was not very difficult actually. So then I started, in fact, I took moon mission design, transfer trajectory design as my PhD. I have been trying for my PhD since my joining in '84, but I could succeed only after 16 years. That is a success I had actually. Before that, of course, I had so many other publications. Again, I tell you, I was delayed. So many opportunities came in for me for PhD, but though it came in search of me, I could not take them because maybe God wanted me to take this as my topic. Otherwise, in '92 itself, low thrust trajectory is the first one I took as the first topic. Then my second topic that was in actually '91, '92 time. Then later on again another opportunity came '94, '96. At that time I thought I should this Lagrangian point, hollow orbit, that type of thing I should work. That also did not happen. Then finally this opportunity came and it worked. Then lunar mission, it worked. So like that, so mission after mission, we started working. Yeah, and after all, I told you about time, spare time. That is the thing. We did not have so many launches to occupy our time. So a lot of spare time was there. And of course, family also cooperative. That also very, very important. So if somebody looks at you and thinking in the house, you may sometimes crash, also as possible. But I was very fortunate enough to have my family background also. So that way we kept on continuing working.
Right. So, sir, as a follow-up of your previous discussion where you actually talked about the Mercury, like you reproduced the Mercury mission trajectory. So I would like to say it was actually the Lambert problem, which was a well-known curious puzzle in the field of orbital mechanics at that time. And the problem dealt with finding a trajectory joining 2 points in space for a given flight duration. So almost equally well known was the Batten solution, which I guess you're talking about, for being one of the most robust yet complicated procedures, and yet you actually ended up implementing within 1 year after joining ISRO. So as a follow-up, like you worked in an era when computers were the size of a room with very little computational powers. So how did it actually affect your experience or your research when you had to solve problems and come up with solutions?
The very fact that the computer power was limited is the motivation to develop analytical techniques where you cannot spend too much time. I used to hear it is running for hours. Numerical solution, it is not coming. And days together, our CFD problems. Lagrangian point missions can run for at that time for days together. It will run and with no solution in sight. So this type of situation was there. That only made people to go for analytical solution, which will serve as a good initial guess for numerical procedure, to start the numerical procedure. That is the whole thing. So that is a big motivation. But when you are talking about batting was not the first method what I implemented. I implemented actually true anomaly iteration, what nowadays I teach my students actually. It's a simple method, true anomaly iteration. That is a method I implemented. Then because starting itself is a complex method, where a lot of other things are there, will be difficult. So first job was to simplify simple method. I studied by many methods and I chose true anomaly iteration finally actually impressed me. It's a simple and only few lines of code will do for that. So I tried that and it worked actually. When I went for batting is actually when we are searching for many opportunities. When we search for opportunities, we will be varying our flight duration, we will be varying departure date, all that. So in that process, we may end up with hyperbolic orbit, we may end up with elliptical orbit, we may end up with some other special types of conics, which we will not know because computer is doing inside. We do not know. It may get stuck up. So we do not know. So a method which must be capable of dealing with all types of scenarios we must have. Batin actually serves that. Then I implemented Batin. Actually, when you are talking about role model, when I went through Batin at that time after joining, because till joining I never knew about Batin. After joining and when I started searching only R.H. Batin, Richard Harvard Batin, he is a great man. I used to think he is the Dronacharya, I am Yakalaiva. Like that I used to think. I should become one like that.
Okay. I would like to ask, when we talked about true anomaly and universal anomaly, it somehow reminded me of the coordinate systems we had to deal with even as students in your class. And we got to know you actually developed a general purpose propagation tool that is capable of handling 16 different coordinate frames. So what was that development cycle, and was it like a part of your process of developing the Batin solution?
What you are talking about is general orbit predictions, GOBS I call software. That was not actually nothing related to Batins or anything. It's a propagation software. So Batin one is determining the conic. This one, GOBS is actually given a conic to study the motion of the spacecraft in that particular conic. That is a GOBS does. This is actually part of my work I carried out during my tenure in DLR, West Germany. At that time it was West Germany. Okay, so DLR is the equivalent of ISRO in West Germany. So I was working there for some time. They wanted to develop some code which is equivalent to Geodyne. Geodyne is a JPL code which takes care of all forces into account and studies the motion of the spacecraft. So they wanted to have their own analysis, this type of code, which is equivalent to Geodyne. This again, at that time we had ISRO DLR collaborative program actually. It's a type of exchange. It was happening. So because of my background in interplanetary missions and all, I had the opportunity to go there and work. So this GOBS is a part of that work there actually, and it, as you said, it handles 16 coordinate systems. Any planet, including Sun, it can study motion about any planet, and also whether it is ecliptic based frame or a Earth equator or planet equator, any planet equator. It handles all that. Everything is embedded in that. So it can study the motion of interplanetary spacecraft, accounting for all forces, including solar radiation, pressure. If there is a drag around some planet, then that drag model, for example, Venus drag model, Mars drag model, Earth drag model, all drag models I have put there. And also Mars non-spherical force, Venus, every planet has its own non-uniform gravity field. Everything is modeled there. So like this, you can study the motion of spacecraft around any planet as well as interplanetary spacecraft. Okay, that's GOBS. Okay.
Mm-hmm. Thanks for that. So this is quite insightful to have an idea about this thing. I mean, someone who has not worked in the field also, it makes quite a lot of intriguing sense. Maybe right now we can jump a little bit, and I would like to ask you something in context. In 2017, as we know, ISRO set the world record for the most number of satellites in single launch with 104 satellites with a PSLV. So this journey of this multi-satellite separation for ISRO began almost 2 decades ago, in 1998, and you were one of the first major contributors in the mission design, as we believe. So would you like to talk about that project and what challenges it brought along for you, and how did you come about the implementation of it?
Yeah, that's right. So anything, first when we start, that fear of unknown will be there. It may look simple. I used to tell in the classroom also, nothing is simple, nothing is obvious, nothing is trivial. We have to take everything seriously. So that time, now we have sent 100 satellites. In 98, we started with 2 satellites, one Korean, one German. I think KitSat and TopSat. 2 things were there along with the IRS. So we had to house them, and immediately the new problem there was actually all of them are released with very small differences in velocity. With IRS and KitSat and small satellites, the velocity difference will be less than 1 meter per second. That is the type of difference between them. So that means they have almost similar energy. So they will be coming back to the same location after one period. Period will not change, because once you say energy is same, period is same for the planet. So where they have started, they tend to come back to the same location, and collision is possible. That is a problem, and you have to inject them with whatever small bands for each of the things available. We have to inject them such that they will not collide with each other in future for a long term, maybe 10 years, 15 years. That was the problem at that time to handle, major problem. Otherwise, even if you launch, if the next thing, even small satellites come back and hits the IRS, then it's a little dangerous situation. We wanted to avoid that. IRS losing is a big problem. It's a very expensive satellite, remote sensing satellite. So that is how that was a challenge, how to release these satellites in such a way that they will not come back and hit the main satellite, and also they will not have collision among themselves. That problem is purely orbit related things. So obviously I have to work on that. So I was actually fond of this type of new problems. Then immediately I grabbed the problem. I started working. As usual, I always look for analytical solutions. Actually, this problem was solved by French people. They actually try a lot of combinations. That means what are the parameters? I would tell you maybe before explaining what are the parameters. The velocity with which we release is the main parameter. Because two fellows are there, one IRS is there, some small satellite like KitSat is there. So if suppose you release with 1 meter per second, a major share will go to KitSat because it's a smaller mass. You know that, that's all mass equilibrium, all that. So they will have small, this one, and it will start moving. And also, in which direction you will separate. There's the second parameter, velocity. With what velocity you will move, release them, and which direction you will release them, and after how much time you will release them. That means release between two satellites. What is the time duration? I release KitSat, then after how much time I should release subsat such that it will not come back and collide with. So these three, first main satellite, then KitSat, then ToughSat. That was the scenario actually. So one after the other we are supposed to release. So these three, with three parameters, French people, what they used to do is actually they play around the parameters. So thousands of combinations you take, and they choose one combination which does not result in collision for a maximum duration. That is a way complex problem they were solving. So I was looking at that, and then I thought I will do it as usual in an analytical way, in a closed form way, which so that it can be quick. I don't need to go for really search for the solution without knowing what is what. Randomly search. That is one way. It's a crude way of doing that. Brute force method we call. But so I found all combinations which will result in collision. I reverse problem I worked out actually. I found out all combinations which will result in collision. Then you choose apart from this. That can be that collision combinations quickly you can get. That is the one method I developed actually. So you draw a curve, that design curve, collision curve, and then you choose any other apart from that. That is actually non-collision thing. That is one way we handled, and that was used also. That KitSat and ToughSat with that the duration and what is the direction. So we turn the vehicle and release. So now IRS is released first in the orbit, and then PSLV fourth stage is oriented either left or right, for some degrees, some angle. It is oriented, then released. Then again by another orientation, turn the vehicle to another orientation and release. That is the thing. So what is that orientation? We have to work out. That's what we did. So that was released, and that mission was successful. First time we made multiple satellites. But now if you think 100 satellites are going, not 200 satellites are there. That is a thing. My colleagues there are still working on that code, whatever code I developed at that time. So you have to put module after module after module after, because it is further another satellite. So you have to put the separate modules, but thing is same, method is almost more or less same. So that is a way. So you have to do it. Only here computational effort has become more. Computationally it becomes expensive and complex. You have to handle. It's not method. Method is simple now because it can handle. Just its method is only just to avoid the thing. The later youngsters developed a lot of things. 100 means yes, I can now do that with computer. Now computers are also fast. You can do all things. So you can always work out a combination resulting in non-collision among themselves.
As a follow-up, I'd like to ask about that part where you actually mentioned that ISRO reoriented the fourth stage in the same orbit, right? So after the reorientation, does the fourth stage continue to go around in the same orbit as the IRS, or was the orbit actually changed?
No, a very small inclination change will be there. When you change the orientation, practically you will not feel the change. If I say it will be 0.01 degree, not 2 degree only, but that is sufficient to push it into a different plane. A plane is different in space, actually 0.01 matters so much. And also, because of this velocity difference and the duration and the period of them is slightly different. So it will not cross, because in the different plane, we are sending them into a different plane, and it's slightly, that energy level is slightly different, and period is different. So they will not come back to the point of release where it was released. They will not come back. First, one fellow will come. Maybe after some time, another fellow will come. After some time, another fellow will come. Like that, it keep on increasing. The distance between relative distance will keep on increasing. So that is the idea. So which combination will do this? But there are dangerous combinations which will lead to exact collision also. There are. That's why we have to be careful. So we have to avoid such combinations and choose one which will build up the relative distances with time.
I was actually also fascinated by the fact that you could find that all combinations which could result in collisions. One thing is, like, you talked about the brute force method and using analytical solutions to find like all possible combinations, but then sometimes it makes me wonder, like, how do you actually end up accounting for all kind of perturbations? Like, space is filled with so much perturbations that you can predict up to a certain limit. But then after 10-15 years, the difference becomes so huge that people end up using computers these days to account for the perturbation effects.
That's a very good question, very highly technical. Fortunately, our satellites are released at a higher altitude.
Right.
So except drag, all other forces will have same effect. They are independent of mass. Maybe solar radiation pressure to certain extent. So whether it is J2 or that is non-spherical Earth or Sun, Moon, all of them will act on the same way all spacecrafts. So the distance between them more or less will be kept the same. So you just study, that's the beauty of this actually. The whole situation will be different if you do it within the atmosphere, because there the area it is exposed, that all that will matter. Heavier fellow will have more this one, and lighter fellow will have lesser drag effect. So that way they may be having anything can happen. That cannot be predicted. So fortunately for our problem, it was outside the atmosphere, or we can say in the weak atmosphere. Now I cannot say completely outside the atmosphere, but it is in the weaker side of the atmosphere. So this type of problem, dealing with the perturbations is not a major issue there. That if you deal with without perturbations, that almost it is applicable for with the perturbations. Of course, with the perturbations, closed form solution is not possible.
Right.
So what we used to do, I have a combination I have worked out. So introduce there all perturbations and then simulate whether it is really affecting. That is the one way to confirm whether this combination works well under perturbations also.
That's like a smart way of not using perturbations, getting a solution, and then using that specific combination to run under a perturbation model to verify. Right.
So this is actually nature. Nature has given us so many simple things actually. We only make it complex actually. If we understand rightly all these simple things, all problems can be solved easily. That's what I believe actually. That's it.
Okay. So yes, definitely with time and the number of satellites we keep launching in a single launch, the complexity of the solution would definitely have been increased multi-folds. Okay, so in 2008, ISRO launched the first Indian lunar probe on the Chandrayaan-1 mission. The mission was a major boost to India's space program as India researched and developed its own technology in order to explore the moon. You had played a significant role as a deputy project leader of this moon impact probe mission, Chandrayaan-1. Would you like to share with us your journey through the Chandrayaan-1 mission conception, design, and development cycle?
Yeah, actual project started in 2004, and actually I said, the work on mission, lunar mission, all that started 94, 96. Before that, interplanetary I told you. Then later we started working on moon mission within our center, Vikram Sarabhai Space Center. That is a thing. We had task teams to shape project, how to go reach moon, all that, what is the type of mass we can reach, what vehicle we can make use of, all that we studied in detail. And we were doing that in 96, 98, that time frame. And slowly it came to a project mode. Took shape to the earlier chairman, Professor Rangan. He is the man who gave shape to all these things. Then Dr. Madhav Nair, he realized this is the way it went on. So when we were doing this Chandrayaan-1, of course Chandrayaan-1 project, this design, all that, fine, how to reach, all that has become clear. Then once sometime our earlier president Kalam ji, Dr. Kalam, he came once to VSSC. He was reviewing this Chandrayaan-1 things and all. We were all presenting, and he said, anyway, you are going so distant place. Why don't you put something on moon surface? He just made this comment. Then immediately we were asked to work out what is the mass we can put on the moon, how to accommodate all that. So already we were running out of mass. Actually, mass budget was very tight. So if we want to add one more module of something, that we worked out that some 35 kgs later on. At that time we were not knowing how much will be required to be, because it is a mini satellite itself. To put all subsystems together, it should work till it goes, isn't it? It should have a power system, communication system, thermal system, everything should be there. It's a mini satellite. So with everything together, minimum some mass must be there. That anyway we worked out later on, and it worked out to be 35 kg. So already with a tight budget for Chandrayaan-1, how to add this was a big issue. Then actually again, as usual, we worked out some strategies which will save some fuel. That is how we worked out one. Anyway, that has not become popular. But initially our strategy was after reaching there, you do orbit reduction. So how we do the orbit reduction, this you can start reducing from perigee. So it goes into 500 by suppose 1000, something like that, 5000, 500 by 5000 initially if you put. So there I want to final orbit 100 by 100. So in many ways you can do it. So normally what we do is actually we first reduce the apogee and then go to apogee, reduce this. Like that we do. But we adopted a different strategy. First we will reduce the perigee. Go to apogee, then reduce the perigee, then you reduce the thing. This saved about 78 kg of fuel. So this strategy, we worked out what to do, how to save all this. So this type of requirement also, it leads to some type of new strategies. Otherwise, because anyway we had it, we would have never thought, because we were more used to GTO to GSO rising. So similar style we thought we will do it. But here little different. Think in a little different way we could save some. We named that apocerinum biasing strategy. Now all other future missions also, I think it's followed actually. So like this, we worked out in so many places. Instead of earlier, we were thinking of targeting 1000. If you target 1000 and then reduce it to 500 unless you need more fuel. So instead you target directly to 500. That saves a lot of fuel. So whether the targeting to 500, what are the complications involved there? So that has to, because navigation has to be very accurate. When you are targeting closer to moon, if any navigation error comes, it judges wrongly, it may result in impact also. So that type of risk was there. So we have to revisit our navigation things, and then we were convinced that 1000 can be easily reduced to 500 and we can make room for some more mass. That's the type of strategies we worked out, and finally we accommodated a moon impact probe also. And Chandrayaan, actually there is a roaring success at that time, because nothing equal to that first success actually.
So, as a follow-up, we know India's Chandrayaan-1 played a crucial role in the discovery of water molecules on the moon. It was indeed Chandrayaan-1's data which showed the evidence for water in the exosphere of the moon. But it was only later that NASA confirmed the discovery of water locked in minerals on the moon using its own moon mineralogy map. So, what do you have to say that we lost the golden opportunity to actually declare to the world our discovery of water on the lunar surface at that time?
Actually, for science, always we need repeatability and proofs. That's a main issue here actually. Of course, what you said, mineralogical mapping, that M3 we call, that also is part of Chandrayaan only. But in fact, MIP itself found water while descending, and we were knowing about that result 2 weeks after that. Our scientists, they analyzed one spectrometer was there, chased. Actually, we were told in a meeting that there is a big result is there, groundbreaking result is there, and but what was it not released? But we all know that it is, we found water, something like that is there, something. It requires, any experiment requires repeatability. But MIP was a one-time experiment. It went and hit, that's it. You cannot repeat that. So for anything to be publicly to be made known, this type of science demands that you have to reprove. Because of that, some delay was there. After M3 has found, we also said, yes, we also created water as back as 1 year before. That something like that, we were to, that confidence. We cannot blame thing also, because always doubts will be there. Some outgassing things are there. You know what is outgassing? It may be so. Maybe water might have deposited on the MIP itself. Your instrument might have measured that. All these type of doubts is natural. We have to prove that there is no outgassing. We have to all that we tried, but still repeatability is a major issue. That's what delayed, I would say, in my opinion, the release of the great result that MIP found water.
Okay, all right, sir. That's quite a quintessential story about how science works in a larger context, and especially regarding the biggest of discoveries. We'd like to tread along the next major chunk of your career trajectory, wherein soon after the launch and success of the Chandrayaan-1 mission, close to 2010, you made a decision to shift to academia as an adjunct professor at IIST. Would you like to talk more about your motivation for shifting from the setup of a scientist to the academic setup as an adjunct professor at IIST at that point in time?
Yeah. So honestly, I was very much disturbed by the fact that even now I think this area, astrodynamics, actually is not very well-known area in India. I know, except in ISRO or maybe parts of DRDO, nowhere else this type of research. Of course, maybe teaching somewhere here and there, yes, certainly going on. But research in this area, serious research actually only goes on in this type of organizations only. So then I was thinking, anyway, I never thought about shifting to academia before IIST came. When the opportunity came, so I thought I can go and maybe generate more people in astrodynamics area. That was the one motivation I think I had. Maybe I succeeded in at least to some extent to that area, because I could enthuse some people at least to work in this area. That is the one satisfaction probably I have for this shifting to academia. And I also know that I am not completely in IIST. Even now I am regular employee of Vikram Sarabhai Space Center only. So that way, my participation in the projects of, like afterwards I participated in Mars Orbiter mission, Chandrayaan-2 mission, so many things. They are always there, because that is always there in my mind. So I thought, why not? My work nature is not going to be affected, and I am going to work with more people with the same kind of problems. With more problems I can work out. And I tell you one more point. When you are in a particular organization, you are restricted to work in restricted some area because some ethics is there. Somebody else will be working in this area and you are not supposed to work. That type of situations will come. When you shift to academia, there's no boundary for your thinking. So that is the one thing I liked actually. So you can work in any area of your liking, of course, within the whatever astrodynamics. So when you shift to academia, you can work with students. That is another thing, and you get as many students depending on my own energy to work with me. Whereas in ISRO, I am with limited manpower because we cannot have for this problem one person, this problem. That is not possible in government setup because it's people's money. We cannot just like that spend that money. So that is another attraction I had. I can work with my students on the same type of problems. Maybe I can expand my areas. That is a major thing. When this opportunity came, actually again I thank God. The opportunity came in search of me because ISC started in Thiruvananthapuram only. I joined probably. Otherwise I don't know what I would have.
That's actually quite a profound take on this idea. On that note, would you like to briefly talk about the kind of research you have carried out in the last few years with your students?
Mostly about different types of missions only. That's because that is the area I am interested in. So we started working with Mars entry missions first, and then landing, and then low thrust missions. That is with ion propulsion, how to reach other planets. There actually again, it's a very good work has been done where you include the gravity fields of planets. That is a very difficult task. The optimal control and patch conics is the marriage between these two. Apart from that, he recently in constellation design worked on lunar mission, how to transfer a spacecraft from Earth to Moon, and actually Lagrangian missions, Aditya mission, because most of the projects I give shape keeping ISRO future missions in mind. So that way Aditya mission to students worked actually developing methodologies to design the transfer trajectory to Lagrangian point, and then maintenance strategies, how to keep them around that, what is a strategy together. Rendezvous missions, you can say shuttle type of thing. It goes and rendezvous with some other module gets in with shuttle. That type of rendezvous problem also we worked out. All these are part of optimal control because my core strength is for any trajectory person, two areas you must be strong: optimal control and optimization. Two things he has to be. So like this, so many landing to Mars landing to Moon landing to Moon transfer to Mars transfer, all the problems like rendezvous problems and Lagrangian point mission problems. Like this, so many problems. I think I lost account, and I will make a list. Maybe I will load it in the website. Some at least 20 problems not repeated so far. I would say that I'm confident.
This was extremely inspiring, sir. Quite a combination of thought-provoking insights of the field, the applications in therein, and even further outside of the subject, what it takes to manifest these ideas in real-life situations. It's difficult. It's really difficult to grasp in the fact that we did not come across these stories and insights over all these years through our books or science magazines or any such. These understandings are extremely precious, and it's been really fortunate to have been able to talk to you and discuss these ideas in such detail. Thanks a lot. Thanks a lot, sir.
Yeah, it's a good initiative. You should keep talking and discussing. Actually, this is the one way the knowledge grows, exchange of knowledges, right? If you keep continuing like these discussions with people, and people will get to know about many things, and slowly it spreads. This is the one way, the propaganda for astrodynamics also. Okay, yeah, that's it. So I am very happy that I could do it with you people. Okay, good. Thank you.
This was Zeroing In with Dr. R.V. Ramanan. It has been brought to you by the Sounding Rocket in collaboration with the IIST Alumni Association from the Indian Institute of Space Science and Technology, Trivandrum. We extend our sincere gratitude to Dr. R.V. Ramanan for taking the time out and talking about the stories of wonder, his beautiful insights and elaborate ideas with us, along with Garima Agarwal and Varshit Reddy for collaborating on this episode. On behalf of the whole Zeroing In team, which included KVNG Vikram, Fenil Shah, Manish Chauhan, Prajwal Patnaik, Shreya Mishra, and I am Naman Jain. Thanks a lot for listening to this episode. If you have any suggestions, you can write to us on zeroingin@outlook.in or contact and follow us on our Instagram handle @zeroinginpodcast or the Sounding Rocket page on Facebook. Thanks a lot for listening to this episode, and we'll meet you on the other side of the week.